Thank you very much for joining us this afternoon. My name's John Allen. I'm joined by Jimmy O'Sullivan, who's head of our commercial department today. Just to warn you, we've had a lot of power outages. It seems to be jumping in and out, unfortunately, all day. We do have backup computers and computers connected to phone hotspots and all that sort of stuff. Inevitably, they'll probably all go wrong when the power goes down, but we'll hopefully stay going. But if it does drop out for a minute, we'll work on getting it back up as soon as possible on maybe another computer. But just bear with us. Today is about commercial PV. I suppose what to expect from today, how solar works. A lot of us are familiar with how it works in general. We've seen a lot of panels on the roof. The kind of the knowledge out there for even from the public is quite high about solar. So we'll be going through that at a very high level. We'll be going through design considerations. Some of that can maybe seem like it's quite simple, but when we go into the details of it, there's maybe more things that need to be considered that people realize. Obviously, planning restrictions isn't a big one, but just to make aware of it, profiles daily and annually, that's probably one of the big things that gets underestimated, and that people don't take into account. Array design, weight considerations. Obviously, we're putting panels on our roofs. We want to make sure that they can take the weight, the wind load of the wind getting under the panels and putting an unexpected load that the roof not mightn't be used to. And electrical and grid connections, important consideration. ESB networks are always juggling grid balancing, trying to balance the amount of electricity that's being generated from our power plants to what's being consumed. They don't necessarily like having these random generators coming onto their grid. So they do analysis to see, okay, are we okay with this 300 kilowatt system being connected to our system, or a 500 kilowatt system, or a 50 kilowatt system? How will that affect the grid? Is the grid strong enough to support that if it does export all that we think it's going to export? So there is a consideration there that needs to be taken into account. And we'll be talking about batteries. Batteries fit into probably the profiles, the annual and daily profile, and taking that into account. We'll also be going through grants. The grants for PV is fairly simple. They can be part of a bigger grant as well for a commercial project. Jimmy might go through that in a bit more detail as well. And we'll be kind of looking at a bit of a case study as well. So as always, there's a Q&A box at the bottom of the screen. If you want to put in your questions, feel free to put them in, get them in early. Jimmy and myself will be looking at them, and we have a colleague outside as well answering questions. So if we'll try and answer them as we're going, if at all possible. And if they're more bespoke, might type a response to them. Going to give you 30 seconds about Ashgrove. That's kind of the only Ashgrove specific part of the presentation. We're in energy since 2001, specifically heat pumps and PV. It would have been solar thermal back in the day, but it's now gone into obviously solar photovoltaic, insulation, windows and doors. We're SEAI grants, so we're registered as a one-stop shop, which is domestic. The CEG is both domestic and commercial, and then the BEH and the Warmer Home Scheme are domestic. We're doing 15 to 20 installs per week, probably slightly more than that, depending on the week, but we're not hindered by weather these days, so it's up at maybe 25-ish. We've a growing office every day. It seems there's new people starting, but we've put a lot of focus on having resources available to answer questions. Speed is one of the things we're trying to improve on. We'll improve it. We can improve it. We're not perfect by any manner of means, but we're always trying to get better. And we've a professional network. We're fortunate. We've a 25 years in business, so we've a strong professional network around the country, particularly with plumbers, BER assessors and architects and engineers and electricians is all growing all the time. We do have pockets where we're not as strong as we'd like to be. So if you're if you're interested in having a chat with us, we'd be delighted to talk to you to see if there's anything that overlaps. Free information. So we have an app, whatgrant.ie, that's based at kind of navigating the various grants, both domestic and commercial, currently getting updated as we speak. But it's to provide kind of quick guides on where you should go depending on what you're looking at. We do a lot of these webinars. At the start of the year, we were aiming to keep it to 100 because there's a lot of time that goes into prepping for them and doing them. So we were trying to keep it to 100. We're probably on for 150 or probably pushing towards 200 by the time the year is out. But we're happy to do them. The main purpose of them is to give good information out there. They're all free. There's CPD points available. We're happy to send out certs if you're looking for them. But what we're trying to do is get information on various topics out into the industry so that more and more people are familiar and more aware of what's available and how to navigate it. So they're not necessarily salesy. Obviously, we're a company and we're hoping that we'll get the bounce of the ball somewhere down the line, but the predominantly they're there to provide good information. And we do live seminars as well. I don't know when the next one is set up for. I think there's a local one here in Mallow, but we'll send you more information about that. So just in very basic terms, 30 seconds about how solar panels work. Again, most people are familiar with them. You have your solar panels on the roof or on the ground. They produce DC electricity. That DC electricity goes into the inverter. In its basic form, the inverter converts that DC electricity to AC and tells that AC electricity whether to go into the building or whether to go back to the grid. So obviously, if there's a load in the building, if there's something calling for electricity in the building, it'll direct the electricity into the building. If there's no load and the building is satisfied, it'll send the electricity back to the grid. Obviously, batteries are becoming a bigger part of that, and that's to align a scenario whereby your production from your solar system doesn't directly align with the consumption of your building, and so you might want to store some of that electricity for later. Batteries aren't limitless, so they're like you can get obviously 100 kilowatt hour battery or 300 kilowatt hour battery. You're getting into expensive territory, but it might not make sense to put in that size, and it will still fill up depending on your system size. So the size of the battery is as important as the size of the solar panels and whether it's useful or worth doing or not. So some of the design considerations that we're looking at, obviously building location and orientation. We all know that south is the ideal orientation for buildings. Not always achievable, and we look at the consequences of that later on. The next thing we're looking at is energy use and consumption profiles. So how does the building consume energy as it stands? And the more data we can get on that, the better we can design the system in order to match that consumption, or at least make good decisions around that consumption. So we look later at half-hourly data for a project and graph that over the course of the year, which allows us then to make good decisions on what we'd recommend to that customer. The MIC or the MEC, maximum import capacity, and the maximum export capacity is an important factor. That's down to your ESB connection and what they're likely to allow you to export. So as a reference point, we look at the maximum import capacity. It tells us at least that in theory, the same could be put back out onto the grid. When the ESB networks are looking at it, they're obviously looking beyond your own building to see, okay, if 10 buildings in this industrial estate put on the same solar system, would the grid be able to handle it? So they'll adjust the maximum export capacity accordingly, but the import capacity as a starting point is a good frame of reference. Nothing to do with PV directly, but when we're talking to customers about solar, we're asking them, is load shifting possible? So is it possible to shift some of the load or the consumption to times when it might be more appropriate for solar? So can we move something that happens maybe at night? We might try and move it to the day. That could be heating large tanks of hot water or something like that. That obviously doesn't impact production in your facility or the workings of your facility. So we spend a lot of time talking about those sort of scenarios with building owners and operators. And the roof structure detail, do we need to get a structural engineer involved to ensure that the panels will the roof will take the extra weight of the panels? Do we need to spread them out a little bit, which we'll show in a video where maybe we don't concentrate it as much in one area and put small gaps between blocks of them to distribute the weight slightly more evenly. Planning permission, they've removed a lot of the obstacles for planning permission. Obviously, they want to get more and more systems onto our grid. So there is these solar safeguard zones, which are located around airfields. Obviously, you have your big airports, your Cork, Dublin, Shannon, but there's smaller airports around the place, and airfields that need to be protected from potential glare from solar systems as well. So they limit for outside of those solar safeguard zones. So everything in white here, there's no limit to the size you can put on your roof. So you can fill your roof with solar panels and there's no planning permission required. If you're putting a ground mounted system on, it does limit it to 25 or 75 meters squared. So that's roughly around 23 kilowatts. So obviously there's more, you're essentially building a new structure. So it's potentially more impactful than just putting solar panels on your roof. So there is a planning permission required if you're going for bigger than that. Inside the solar safeguard zones, so inside these blue dots, they have a 300 meters squared limit of solar panels for putting on your roof. So that's roughly around 90 kilowatts. And the same 75 meters squared applies for ground mounted system. So there is planning permission required in some cases, but it's very rare. I don't think we've ever had a system that's required planning permission. Most of what we're dealing with is ground mounted systems, and the roof mounted systems we're dealing with are, sorry, most of what we're dealing with is roof mounted systems. And the ground mounted systems we're dealing with are typically kind of 15 to 20 kilowatts. So that's it on kind of planning. We're going to go into the profiles, and I'm going to let Jimmy take over and give you his expertise in that area.
Yeah, thanks, Johnny. Okay, so looking at the profile, so obviously the solar PV will only generate electricity when the sun is shining. So if we were to picture it, it'll be a bell-shaped curve. Bell-shaped curve from January to February, or sorry, January to December, where the maximum amount of solar PV yield will be during the summer months or daylight hours. What's good to note as well is that direct sunlight isn't actually necessary for the solar PV panels to generate electricity. They will work off direct radiation and indirect radiation, which they call diffuse radiation. So as long as it's daylight hours, there will be some yield from the solar PV panels. So when we're looking at potential buildings or potential systems, so if someone comes to us, the first thing we will ask them is for their electricity bills. So then we can see what their profile looks like, and we can quickly tell them, are they an ideal candidate or a non-ideal candidate, I would say, for solar PV. So the one we're looking at here, it's 200,000 kilowatt hours over the course of the year. But what we can see is that they're very much a non-ideal scenario when it comes to solar PV consumption, I would say. So their loads are peaking January, February, March, and dipping in the summer months, and then increasing during the winter months. So what this likely is, this particular building would probably have a lot of heating load that would be direct electrical. It could be a heat pump system or whatever it might be. So it would be a non-ideal scenario. So if we were to install, say, a high capacity solar PV system, which we will look at shortly, they would actually end up exporting a lot of that at a lower rate than what you would buy electricity from the grid for. But again, we can see what the benefits and disadvantages of that would be.
The important thing I think is there, it's not that you shouldn't get solar in
Yeah.
this scenario. It's just that you should design it specifically. So it's still suitable for solar, but you need to take into account your profile when you're designing it.
Yes, exactly. Yeah. So when we see a candidate like this, so when they're peaking during the summer months, so this could be, say, a milk processing plant or anything like that that's following the trend of the milking season essentially, or they might be an office building where there's a lot of cooling demand. So a lot of chillers running through the summer. Again, this would be a more ideal scenario than what we would have seen previously. So they would probably end up consuming a lot more of what is generated from the solar PV as opposed to exporting it. So those are some of the things we look at a very high level at the very initial stage of engagement, I would say, when it comes to solar PV systems in the commercial space. When we look at the orientation of the panels and the different angle inclinations as well, we can see what is best and what's not ideal. But I suppose the message here is that the impact of the orientation, so the orientation being, is it south facing, west facing, east facing, or north facing, or a combination of some, the impact isn't as large as probably is thought of. So I think the gut feeling out there from a lot of people is that it has to be a south facing roof. That's not necessarily the case, and we can look at that. So the black dot here shows an exactly south facing panel essentially, and the angle that it's at. So this is the angle that it's from the flat. So this one is at 10, 20, 30. It's at about 35 degrees here. So that's hitting about 100% of what that panel can output, essentially, excluding the losses. So as you can see, as we reduce that angle, so we get to a more and more flat roof. So a lot of commercial buildings these days would be anywhere between 10 and 15 degrees. At about 15 degrees, you're still in that sweet spot, where you're going to be maximizing the output from that panel. As that panel gets more and more flat, you're still going to be at 90% plus of what that can output. Now, if we were to take that scenario where we've actually looked at a building only last week where they have a very large pitched roof, but the pitch is only 10 to 12 degrees, so it's quite minimal. We can even fill their north-facing roof. So looking at this chart here, if we fill that north-facing roof as well as the south, so they'll get about, and it's about 15 degrees, 10, 12 degrees. So we're at about 95 to 100% of your output for the south side. And on the northern side, you're just hovering around the 80% mark there. So it's not a massive amount of drop in output when it's compared to the south side. Where this, in the past, this probably would have been more of an issue, largely down to the cost of the solar PV panels. So the PV panels themselves were very, very expensive in the kit to go with it. So you would only optimize and put the location of the panels where it makes most sense, where you're going to get the best bang for your buck. But because the panels price has decreased and decreased over the years, it's not as much of a financial impact. You're still going to get 80% of the output yield for a relatively modest additional increase in the investment. So when we're looking at this then, if this X then is showing kind of a directly east-facing panel, again at the same angle, it's still about 82, 83% of the output than what the ideal scenario is here. So where we'd see that a lot is any east-west facing roof, so no direct south-facing one, and the east and west will actually give you the same amount, more or less. So where you might have the shift patterns or anything like that, where you might have a morning peak and an evening peak, where if you take again the agricultural sector, so a milking parlour, for example, They milk in the morning, milk in the evening, so they'll have this double peak impact essentially, where they'll have a reduced consumption during the day when the sun is at its highest down in the south. So in those scenarios, it might be ideal. And again, and as you come southeast, then as well, the output there will start increasing up to that 100% mark. So these are the types of things that we'd look at. So we'd first look at the bills, what kind of a consumption profile that you would have over the year. And then we very quickly, just using the air code, Google Maps, Google Earth, we can quickly see where we're going to land on this, you know. Is it flat? How flat is it? How pitched is the roof? And what orientation that we can look at? Is there any obstacles in the way as well? So those are just some of the considerations that we take on board. Uh, when we look at this, so I suppose this is a video here that I play and talk over. So I suppose the background to this is that this isn't just a guessing game that we're playing here. It's kind of, as soon as we get a query in, we ask for the bills. We can do a very, very high level budget cost, but then if we need to look at that in more detail, we can do that. So we have a team of technical engineers, we have a design team, documentation team, commissioning team, etc. But our design team look at this. So this is the software that they use. So this software essentially takes, I think it's 10 to 20 years of solar radiation data for any location on Earth. So we can select the exact location of the building. We can build that building within the software, so put the correct orientation on it, the angle of the roof. We can put any obstacles that will include shading or impose shading on the building, and we can run that essentially. So what we can do here is, I'll let this play. We put in the monthly energy consumption, and in that there, we're able to then, once we've that in, we can select the day usage. So in this case, we are selecting for the weekday usage the middle of the day. So this exact scenario, we use this for a golf club where they obviously have a breakfast service in the morning, but it's not quite busy. But as they go down in the evening, they have kind of an evening peak there. So that was their restaurants, etc. And then we can, sorry, that was the weekend, and we can change those profiles to suit the activities and the occupancy schedules that we have, or that most suits the building, to ensure that we're giving the most accurate output for that individual building and array design, I suppose. So this is a building. Our engineers then can build up this. This is quite a simple pitched roof. So very quickly we can add in a system here. So what we're looking at here is just the panels being added. So we select typically, I think it's left in 470 or 480 watt panels. And then we can just start laying out these onto the roof. And as we see this, what we'll see here now is the kilowatt rating comes out, and this will then automatically generate the kilowatt hours. So you can see the kilowatt hours here, and this is the annual kilowatt hours that is coming out here. As we build that up, so if we have the bills, say it's 200,000 kilowatt hours, we can simply build the system to match that. So that's only the very first stage. We don't necessarily want to match the exact annual load, and I'll go through that in a bit of detail. So what we're looking at here is the annual output. This is an 87 panel system. We can automatically then do the string design, so the optimal combination of panels in terms of the efficiency from going from DC to AC, and this will then automatically select any type of inverter that we would like. So what we can do then is we can come down here quickly and see, this is just a kind of a sample. So in this particular one, so we're now looking at the summer profile, a typical summer profile. So when you're below the line, this is where you're consuming energy, is the black line. The solar yield is there in yellow, and what is being exported to the grid is there in red. And you'll see as we change through the seasons, that profile will change as well. So minimal or no export during the autumn and winter months then essentially. So what we can do then, our engineers will go back into the system. They'll duplicate that system, and we can add in any combination of panels, any combination of inverters, and in this case, any combination of batteries as well. So we can see, because we saw in the summer there was quite a bit of export going on, we can then install a number of batteries to see what impact they're going to have on the system. So essentially, when we're designing these, typically when we're looking at commercial buildings, we give anywhere between 2 and 4 options, and that will include, different panel arrays, different battery setups or different combinations of batteries as well, just to ensure that we've looked at all different scenarios and get the best bang for buck and what's the most optimal scenario in that case. So in this case, this is the one that's going looking at the battery. So there's actual minimal impact on the savings in this case. So the battery. So in this case, you can see in spring and winter, there was actually no use of the battery because there was no excess solar generation because of the winter profile, or lack of consumption during the winter months and also the lack of yield as well. So what you see here is in the spring months, we see that there's some charging happens where there would have been export of the battery in blue, and then this discharges during the peak hours, maybe between 5 and 7 p.m. in the evening. So trying to reduce the impact of the energy costs around that time. Similarly, you see in the summer, obviously more solar available, slightly more export, but at the same time, we're getting more out of the batteries as well. So what you'll see is the self-consumption will start going up in the cases where we add batteries. And we can kind of see then, do we get the economies of scale by adding more batteries? Simply go back into the design. We can add any amount of batteries and see, okay, now we're got to the point of diminishing returns, so we can start trimming back or alternatively going the other way, essentially. So what this is just showing, again, we've gone back, we've doubled the amount of the number of batteries, and you can see what impact it has there. That actually went from a self-consumption in the summer of 77% to about 83%. So the addition of one battery increased the self-consumption in that case by 5%, 6% even. So that's just to show that there's a lot of science gone into the background. We can then extract that data as well from the software into hourly data, and we can also, at that point as well, we can also input the hourly data if it is available from that particular site. So any site that has, I think it's an MCC10 meter, or certainly has a quarter hourly meter, we can obtain the hourly data directly from ESB networks on your behalf. Just request the MRSO data. All we need is the MPRN essentially. We'll get the half hourly data, and then we can model it out and look at that. And what we'll show is kind of where we'll take an engineered approach then. To give an example of what an engineered approach might look like. So this is actually hourly consumption for a building that we're looking at in Limerick City, just outside Limerick City. So you can see that the profile here, so there's 1 to 8,760. So there's 8,760 hours. So this is the 1st of January, the first hour on the 1st of January. Obviously down to the 31st of December. So what can you see is there's quite a high base load. In the first few months of the year, it was reduced, and then it starts creeping up in the winter. So in this particular case, there is a bit of direct electrical heating. And what you're seeing is the individual spikes here. So these are the weekdays. So this is when staff are coming in, kind of the Monday to Friday staff are coming in, 8 to 6. So we're seeing those spikes essentially. So this particular building is consuming about 599,000 kilowatt hours. Now, so what typically happens is, it just so happened that in this case, we were able to fit 650 kilowatts of solar PV on the roof. But what this profile is telling us now, in the background, that dark color there is the consumption of the site. So our engineers will look at this and go into a bit of detail on it. The green, kind of light green, is the hourly solar PV yield throughout the year, and you can see it follows that bell-shaped curve, obviously, as the daylight hours increase during the summer, etc. But what you see at the red here is export. So there's quite a large amount of export. So in this case, we see, if we go back, it might be easier to read, they're kind of peaking at about 150 kilowatts. So during the summer, the base load is about 50 to 100 kilowatts, where it peaks. And in this case, the 650 kilowatt system is going to peak probably just shy of 600, just taking into account direct sunlight, etc., inefficiencies or losses in the system as well. So at times, in this particular case, we're potentially exporting over 400 kilowatts any given hour during the summer months. So this can be quite wasteful. So in the building, it consumes 599,000 599,000 kilowatt hours. A 650 kilowatt system, over the year, it will actually generate 575,000 kilowatt hours. I think that's about 94 to 97% of that, so it's very, very close. But however, it only offsets 246,000 kilowatt hours. So in this case, 41%. So we're not getting the benefit, I suppose. So it's generating nearly the same amount of consumption, but it's only offsetting 41%
Yeah.
of that.
And I think that's kind of a common misconception out there, is that I'm consuming 599,000 kilowatt hours, and therefore I should put in a PV system that produces 599,000 kilowatt hours, or as close to it as I can get. And that's not always the case, because you can see here it would only reduce their electricity bill by that 246,000. So they'd still be paying for, quick maths, 253,000 kilowatt hours of electricity over the course of the year. They would be exporting, and they can sell that back to the grid at the moment, and it's looked like they'll be able to sell that back for the next 7 or 8 years at least. But you don't want to be relying on that as a payback, that there's a small bit of uncertainty around that. So might not necessarily be the right thing to do. By the way, if they tell us they want 650 kilowatt panels, that's no problem. We'll put it in. We're happy to put that in for them. But we try to provide as much data as we can to allow people to make good decisions. We don't expect everybody to be experts in this. We live in it every day, and love doing hourly data graphs that show peaks and troughs. But in fairness, everybody else has their own day job that they have to go and do. So we don't expect people to be experts in this, but we try to put good data in front of them that allows them to make good decisions.
Yeah, absolutely. Thanks, John. So on that then, if we look at a 300 kilowatt system for that same profile, we can see we're still overproducing, but we've reduced the export in a lot of cases here to no more than 200. So we've halved it essentially, obviously. So again, in this particular case, it's 599,000 kilowatt hours, so the same consumption, a 300 kilowatt system, so less than half the size of what was originally proposed. That's 264,560 is what it offsets. What it generates. So it's just about half, but it offsets 31%. So if we were to compare that, so by doubling the size of the system, more than doubling it, so if we go 300 kilowatts up to 650 kilowatts, we're only increasing the offset by 10%, so 31 to 41% in the case of the 650 kilowatts. So you're doubling the amount of panels, i.e. you're doubling essentially the capital cost of that portion of the construction project, for only a minimal return, essentially. Now, as John said, you can get the export rates, etc., but it's not guaranteed to last forever, and it's at a much lower rate. So I'd rather be offsetting the money or the energy that you're paying for, as opposed to exporting it back. And in this case as well, if we were to try and utilize all of the excess or exported kilowatts in the case of the 650 kilowatts, we're now installing a large amount of batteries, which can be quite expensive. In this case, in the case of the 300 kilowatts, we're after halving the capital cost, and only reducing our offsetting amount by 10%. The investment associated with trying to capture all of this exported energy in batteries is after more or less halving as well. So that's why, biggest isn't best. In certain scenarios, we need to take a kind of an engineered approach and look at that in quite a bit more detail. This again is the same building. So that shaded blue in the back is the building consumption. And I've kept this at 600 kilowatts, obviously, because I wanted to show the scale on this essentially. So what we see is the 300 kilowatt system then in this particular week. So this was a week, I think it was around May, June. So it was a high daylight week. You can see the yield, and where it's above that, we're exporting to the grid essentially. So you can see this is obviously Monday through to Sunday. And in these particular days, there, it might have been less daylight or direct daylight, etc. So it's slightly less. So we had a very good day here. But again, we're exporting the most here. But when we look at that in the 650 kilowatts, we're more than doubling the export in certain cases here. So we're going here from 100 kilowatts to maybe 250 kilowatts in that stage. So this is the kind of detail that we look at. So we'll typically look at it over a year. We'll step back initially, look at it from an annual point of view, then we look at it from a monthly point of view, we start sizing, and then once we're kind of getting into the nitty-gritty detail, we'll start looking at the hourly data. So we'll pick kind of sample weeks, and we can even look at that over a year as well. So this case study, here was this.
Yeah, so this is, I'll take over from here. I'll give you a break.
Awesome.
This is just a system that we look at. We look at kind of, it's been installed, it's a 300 kilowatt system that's been installed. And again, you can see here the approach we took in terms of self-consumption to export to grid. So 71% of it was designed for 71% self-consumption. We have some data, not complete data for a full year, unfortunately, because it was only installed halfway through February. But you can see the actual self-consumption increased because they did a lot of load shifting. Following our conversations with them, they had shifted an awful lot of their water heating to nighttime because they were using night rate electricity and it was cheaper for that. After we spoke to them, they were able to shift an awful lot of that to heating it during the day when the solar system, instead of exporting electricity, it went towards heating that water. So you can see what was fed back to the grid was actually was reduced significantly compared to what the original design showed. So all that resulted in this system saving about 58,000 euro a year. This is actual, designed, installed, and operating. That's based on a 22 cent per kilowatt hour. They're obviously quite a large energy consumer, so they can negotiate quite good rates. After the SEAI grant, the cost of that system was 142,000. So it's less than a 3-year payback, 2.6 or 2.7 year payback. So they're very happy with their system. Just to go through what the grant was for that system. So the grant is from SEAI. It's there to incentivize people to put up solar. There is a domestic version as well. The commercial is a separate entity. And the commercial grant obviously goes up to a much bigger system. You can get it up for 100 or 1,000 kilowatts peak, so 1 megawatt. And your rates are there. So for 1 kilowatt, you're getting 900 euro. All the way up to, if you get between 200 and a megawatt, you're getting 150 euro per kilowatt peak. So obviously you multiply all this out. If you've there's some examples here. If you're getting a 30 kilowatt peak system, you're getting 8,600 euro. The max grant you can get if you're putting in a megawatt is 162,000 euro. So the bigger you put in, the cheaper your solar gets per kilowatt peak, and the less grant you get accordingly. So that system was a 300 kilowatt system, so they got 57,000 of a grant from SEAI. So it was basically a quarter funded by SEAI, and it was less than a 3-year payback. So very happy with their system, thankfully. This is what the online portal looks like. There's loads of different inverter brands out there. We're not going to talk about specific ones today. We have ones that we use. We're happy with SIG. We use Huawei. We use GoodWe. We have kind of a few different ones that we use. But no matter what one you use, the principles remain the same. And a lot of them have this portal in the background. Again, the interface is slightly different, but a lot of the data is the same. Shows you how much the solar is generating in this instance. So this isn't live, this is a recording. But they were producing 187 kilowatts. 160 kilowatts of that was going into the building. They were consuming that at the time, and 27 kilowatts was going back to the grid. So that's what was happening in that instance. And you can see a graph here showing how that happens over the course of the day, and you can look at it over the course of the month, year, lifetime, etc. So that's just a picture of what you can get. Typically, what happens is people get really interested in these for the first 3 or 4 months, and then the novelty kind of wears off. But the data is there, and it also allows us to check on the status of systems in the background. So we have a team here who look after, I suppose, servicing and post sales. And they monitor these systems. They get alerts when a system goes down, and so they can inform you if the system goes down if you're not aware of it, and also troubleshoot any issues remotely where possible. So the online portal is very useful. In terms of export capacity, so we spoke earlier about the MIC, the maximum import capacity, and the MEC, maximum export capacity. The MIC is a good reference point for us to use in terms of what we are likely to get approval for to go back out onto the grid. So if you have an MIC of 50 kilowatts, there's no real point, unless we have a conversation with ESB, which we're happy to have, in us putting in an application for a 200 kilowatt inverter. You have to increase your MEC, your maximum export capacity, significantly, and they're only currently you're only consuming the 50 kilowatts in terms of import capacity. So it doesn't make sense probably from a consumption point of view, but it's a difficult conversation with ESB networks as well to have in terms of why are you looking for such a big export capacity when you're only importing 50 kilowatts at any one time. So the MIC is typically on the bill. So whoever your electricity supplier is, you probably see this is 340 kVA. We're going to assume kVA and kilowatts are the same. For the purpose of this conversation, there obviously is a power factor that can be taken into account to convert them, but they're roughly in around the same. So we applied for, in this case, 200 kilowatt inverter, I think in this case, and got approval for it, and they were happy with that. What that application form looks like, so it depends on the size of the system that you're going for. There's a different form that your electricity supplier should fill out, not necessarily you, but just that you're aware of it. The smallest form is the NC6. That's what we're using on domestic applications all the time. NC6 is basically a notification form. So all you're doing is submitting the form test to ESB networks, and they're saying, "Grant, we've received your form," and acknowledge it. There's no really approval or rejection at that scale, but all you can put in is a 5.5 kilowatt inverter or an 11 kilowatt inverter at 3-phase. So they're the maximum size inverters you can put in for those. If you go above that, if you're going up to 17 kilowatt inverter in single phase or 50 kilowatt inverter 3-phase, you're into an NC7. That's there is an approval process with that, so they do want to check to see, okay, can the grid take what you want to put out, and there is a cost associated with that as well. It's roughly €1,000. I think it's €977. And they will tell you yes or no, or they might say, we're not going to give you the 50 kilowatts, we'll give you 35 kilowatts or something like that. When you're going above the 50 kilowatts, then you're into NC8 or NC5 territory, and you're also into territory where they want more control over what the quality of the electricity that you're putting back onto the grid. So there's frequency monitoring that needs to happen and all that sort of stuff to make sure that that the quality of electricity that you're putting on doesn't upset the frequency of the electricity and the rest of the grid. So you're into bigger kit. There's a cost. I think the cost for the NC8 is €1,300 or something like that. But there's bigger kit that needs to go with it, which increase your capital costs of your installs as well. So you don't ever really want to be just above the bandwidth, if you like, or the grade. You don't want to be at 51 kilowatts and go for an NC8. You're much better actually to put in a 50 kilowatt inverter. Okay, you can't convert as much electricity, but your capital costs are reduced significantly. Whereas if you're going for 150 kilowatts, it now makes sense to go for the larger NC8 application. So that's DSB, why they care about it, and what we need to do. Again, a lot of those forms, they're for your installer to install or to apply or to complete and to submit to SEAI, not necessarily for you to care about. These are just some pictures of installs to give you a feel. Again, you can see panels here going on a corrugated roof. Most of the commercial systems we're installing are going on these types of roof, but obviously there's different brackets depending on the type. This is a 100 kilowatt inverter. So you can see it's a sizable bit of kit, and there's sizable cables that need to go to it as well. This is the panels being installed, so you can see micro arrays here fixed onto your roof, and your panels sit down in that and clip onto it. Ground mounted systems, there's a number of different options for ground mounted systems. So screw system, the screws are put into the ground, and your frame then sits on top of that. This is just a mock-up of what the bracket looks like. Your screw is going into the ground, and you have these slots then that you can bolt the frame to the screws, to the top of the screws. Obviously the slots give you a little bit of flexibility in terms of install. And this is just a small ground mounted system on a concrete pad. Again, depends on kind of preferences and maybe soil conditions, whether you want to pour a concrete pad or if you're happy to go with the screwed system. This is on it was a piggery actually. We installed this system. An awful lot of ammonia in this particular system, which we had to take into account. So all the trunking is actually steel, and the panels are all glass to glass or bifacial panels. They're properly sealed to make sure no ammonia gets into it for the longevity of the system. And the conduits being in metal is unfortunately to stop rodents gnawing at them, which is a nice image. But yeah, all that gets taken into account. Design. This is a slightly different to the micro rail system, but a similar approach. You're fixing your rails down into the substructure below, and your rails then are sitting on it, and then the panels sit on the rails. Another picture of more of them. This is a flat roof system. You can see there's quite a high parapet on this system, which can result in shading, particularly along the panels at the edge. And what we did in this scenario then was allow for optimizers to be fitted to those panels. As there's shading on one panel, it can bring down all the panels on the string, and we don't want the full string to go out. So the optimizers allow that panel to be isolated as there's shading on that, but the rest of the string to perform. So another consideration to take into account when there is shading, that can be trees or chimneys or flues or anything like that that might pass over a specific panel. It can be worthwhile if we decide it's worthwhile to install a panel in that shaded area, we can optimize it to make sure that when the shading does happen, it doesn't bring down the rest of the panels around it. So that's I think it. Jimmy, do you have anything interesting or innovative to add?
I suppose the one thing on the grants actually,
Sorry, yes.
the SEI grant, it has a standalone non-domestic microgeneration grant. Now, because it's based on a per kilowatt basis, it's only based on the kilowatt peak that's on the roof. So, say if it's a 100 kilowatt peak system, that's what's based on the grant, or that's what the grant is based on. So you'll get the same amount of grant for that if you have 0 batteries or if you have 10 batteries. So just to be aware of that. So where we typically see that grant falling when it comes to percentage wise, it could be anywhere between 18-20% up to maybe 35%, depending on the combination of batteries, etc. Um, and if you're going with a larger project where, it's say a full refurbishment of a building where you're replacing roof, insulating walls, windows, putting in a heat pump, uh, and doing solar PV, um, we would probably push that down the community energy grant route. Um, and in that particular grant route, they cap the solar at 20%, regardless if it's a charity or a business or anything like that. But it might make sense, even though it might be less of a grant, it might make sense to pull it in just to get that grant value up, say, for the SEI. It's just something to watch out. But again, that's
Yeah,
the stuff that we take care of in the
yeah,
background.
yeah. But it's worth bearing in mind that the individual solar grant, if you're getting other works done, it might not be the best approach. Solar can add value to the grant for the rest of the works that you're doing, if you like. But yeah, we find that a lot of people get offended when we ask them when they ring in looking for a solar on their system, are you doing any other works? They think we're trying to upsell them something, but in reality, we could use this to unlock other grants for the windows and doors for your premises, or if you were doing re-roofing it with an insulated panel on your roof or anything like that, we can look at getting grants for that, or replacing pumps or compressors or
Yeah.
anything like that if you're in a process environment. So there is other grants available for commercial buildings. Jimmy's the expert on those in terms of which is the best approach depending on what you're looking at doing. But the solar PV one, if you are looking at just putting solar up on your business, it's quite a simple route. I'll just go through the events so that we have coming up the next webinar. So on Tuesday after the bank holiday, we have the one-stop shop, pros, cons, and alternatives. That's for domestic houses. We look at on the 5th of June, which is Friday, we're looking at insulation and ventilation upgrades, issues and solutions. So that's looking at the various problems, I suppose, and again, it's at a domestic scale. We often undervalue ventilation in our houses significantly and try to seal up everything as much as we can, which is great for heat loss. And as nerds, we love that. But there's no point if the building isn't healthy or a healthy place to live. So ventilation, the importance of it, and kind of we'll be going through that in more detail. The 9th then is Tuesday evening at 5 o'clock. We'll be going through domestic PV. So similar presentation, but looking at domestic instead of commercial. The 13th of June, we have a seminar on Future Proof Your Home that's in Mallow. On the 19th of June, we're doing the traditional homes pilot. Again, that's another webinar, domestic scale, kind of pre-1940s and stone walls is a difficult element to treat from an insulation point of view. So there is a pilot scheme out there that SEI have introduced, and we'll be just going through how that works and the impact of it. On the 26th of June, then Jimmy is doing energy upgrade grants for businesses.
Yeah. Yeah, so that's anything if you're businesses is probably a catch-all for communities, clubs, charities, not-for-profits, approved housing bodies, anything other than a house, essentially. So we'll cover everything from there, grants from 10% up to 50% for all of those as well.
And then the 3rd of July, then we have in-person heat pump training, primarily for plumbers and maybe electricians. If there is any BER assessors or anything who who are interested to attend, drop us a line. We do have limited number of spaces, but we're happy to allow people from maybe outside the industry. There's an awful lot of poor knowledge in there around heat pumps, how they work, and how they can be controlled. So we go through that in person here. We have a rig set up to allow us to manipulate flow rates and all that sort of stuff. So that's on the 3rd of July here in Mallow. As I said, primarily aimed at plumbers and electricians who are directly installing it. Will be quite technical. But if we've spaces, and if there's BR assessors or architects or engineers or any other industry professionals who are interested in coming in, listening to us talk about pumps for a few hours, you're more than welcome to drop us a line. This is the calendar. It's on our website where you can book any of these webinars. If you click on the date, it'll bring you to the link to register. So feel free to register for any of them. They're all free. We're doing a lot of them. As we said, we will be releasing July, August, and September calendar the next week, I'd say. And that's it. We'll send out CPD points. There's a couple of people looking for the certs. We'll send out those certs. It'll be next week after the bank holiday, Monday or Tuesday or Wednesday, sorry. And there's a couple more people looking for the slides as well. We're happy to send those out. That's it from me.
Yeah.
Super. Excellent. Thanks very much for joining us. Enjoy your bank holiday weekend, and hopefully the sun stays shining. Cheers.